Good morning. In this short video, I'm going to illustrate my research on inductive power transmission for electric vehicles during the motion. But, first of all, I introduce myself. My name is Vincenzo Cirimele, and I'm a student of the PhD in Electronics Engineering of the Politecnico di Torino. My research tries to investigate a possible solution for the development of an electric mobility, starting from the question: what is blocking the electrical vehicle diffusion? Compared to the vehicle with internal combustion engine, electrical vehicles are more efficient, with a lower cost of energy per kilometer and without emissions. That means a better quality of the environment in urban areas. Moreover, electric cars have a natural admirable dynamic thanks to the intrinsic characteristic of electric motors. Unfortunately, there is still a big problem: the battery. Batteries for traction are still too expensive, and they need for frequent and long stops for the recharge. My research focuses on a solution to overcome this problem called Inductive Power Transfer, or simply IPT. IPT for electric vehicles is based on the inductive coupling between a transmitting coil fixed on or under the ground and a receiving coil mounted under the vehicle. As the typical air gap between the coils ranges from 15 to 30 centimeters, the system has to operate at a frequency of decades of kilohertz to make up for the weak coupling. At these frequencies, the inductive impedance of both coils have to be compensated through the insertion of capacitors to improve the power transfer capabilities. This implies that IPT systems are resonance systems. The installation of more subsequent transmitters can allow the charge of vehicles during the motion, meaning to ideally eliminate the necessity of stops for the recharge and a possible reduction of the battery capacity on board. My research on IPT is framed within two European projects, EcoFEV and Fabric, both financed inside the 7th Framework Program of Research, and in cooperation with several partners. The main goal of my research is the development of an IPT system for a light commercial vehicle oriented to the private transports. The results are providing important indication about the realization of new concept of road infrastructure addressed to the development of a full electric mobility. Let me go through the personal contribution in this domain. They started to the creation of a novel magnetic structure for the receiver. It has been developed through an optimization process on a domain of 13 variables with the different goals of minimization of losses on the coil shield and in the vehicle chassis, the maximization of the coupling between transmitter and receiver, trying to use a limited volume of ferromagnetic material. The optimization has been based on a differential evolutionary strategy. The results have been adapted for the mechanical integration on vehicle board, and you can see the final realization. The structure has been integrated in a laboratory prototype for the emulation of the vehicle movement. It is completely automatized and allows the control of the coil's misalignment along 3 axes. The prototype has a rated power of 20 kW and works with a switching frequency of 85 kHz. The maximum measured efficiency has been equal to 91%. Together with the laboratory prototype, the installation of a non-road prototype is ongoing. We named our solution Polito Charge While Driving. It consists in a charging lane of 100 meters long, made up of 50 transmitters 1.5 meters long. The creation of the prototype involved also the design of a proper electrical infrastructure and the research of techniques and architectures for the interface of the IPT system with the electrical network, the mechanical integration on vehicle board, and the individuation and testing of proper techniques and materials for the installation on the road infrastructure. The more recent activities have aimed to the creation of a methodology for the evaluation of the safety of the application with respect to the protection of people against the magnetic field involved in the charge process. This work has been conducted in cooperation with the Laboratoire de Génie électrique et d'électronique de Paris, where I spent 1 year in the frame of a co-tutelage agreement with the University Paris-Saclay. This methodology is based on the guidelines of International Commission on Non-Ionizing Radiation that considers a limit on the induction value and a more stringent one on the induced effects on the human tissues. A model of the vehicle for the electromagnetic simulation has been created and simplified step by step in order to isolate the only parts of the chassis interested by the flowing of induced current. Adequate problem formulation are applied in order to obtain a fast and robust simulation, avoiding to operate with a huge number of elements. A first phase of simulation allowed to individuate the worst-case condition in terms of induction level. If the reference levels are exceeded, the effects on the human body are investigated through a human model, evaluating the maximum induced electric field in 84 different tissues. The results show as the application is perfectly compliant. The results of my activities appear in 12 international conference proceedings and 2 international journal papers. We can ask me for a complete reference list by email. The complete system on road will be tested in the next month, but I hope that my work is given a small contribution to the development of a technology that will have a positive impact on the future society. Thank you.